Let's now look at the chain rule for partial derivatives. In one dimension, if y is a function of x and x is a function of t, then dy by dt is just given by dy dx, dx dt. Very familiar now as a chain rule. Now, in two and more variables, how does this rule change? It actually depends on the circumstance. Let's consider a function of two variables, z equals f of x and y, and let's say x and y are related to a single parameter t. Then this implies that actually z can be thought of as a function of t. The interpretation of a situation like this is x and y give you a parametric curve in the xy plane, and if we trace that parametric curve out on the surface given by z equals f of x and y, this gives you a curve in space. And on that curve in space, we can find the derivative using the chain rule. It's a bit like if you take a walk on a hill, one traverses the different gradients along the hill, and that forms a path through space. And if we want to find the change in height or the slope of that path in space, we would use a chain rule. And the rule for calculating the derivative along this path, along the surface z equals f of x and y, is dz by dt is the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times dy by dt. And note where we've used partial derivatives versus normal derivatives here. Let's illustrate this with a few examples. So given the function z equals x cubed y minus y cubed x squared, let's find the change of this function as we move around the unit circle. So that is, from a top-down view of the function, we want to move around the circle in this direction and ask how does the function change. We calculate the partial derivative with respect to x times the derivative of x with respect to theta, which is minus sine theta, plus the derivative of z with respect to y times the derivative of y with respect to theta, which is cos theta. So I would then either write everything in terms of theta or everything in terms of x and y and evaluate it on the unit circle. So this tidies up to on the circle only. Let's look at the paraboloid and the hyperbolic paraboloid again. So on the circle, let's do the same thing. So we now have 2x as a derivative of z with respect to x times dx by d theta, which is minus sine theta, plus 2y cos theta, and this is equal to minus 2xy plus 2yx, which is just 0. What does that mean? Well, it means as we move around a circle, the function height doesn't change. And in fact, for this function, that's true for any circle centered at the origin. Let's try for the hyperbolic case. So this is equal to 4xy, it's definitely not 0, and this becomes 2 sine 2 theta. So as we move around the circle on this hyperbolic paraboloid, we have a change in the height. As we go one full revolution around the surface, the change in z goes through 2 cycles of the sine function. In fact, we've actually seen something like the chain rule happening already. Let's consider implicit differentiation again. We can actually use the chain rule now to do this. When we were looking at implicit differentiation, we would consider functions of one variable, y equals f of x, where y is not given explicitly in that form, it's given implicitly. We found using the technique of implicit differentiation how to calculate dy by dx. We can actually now do that using partial derivatives instead. Let's just recall that in our language of multivariable calculus, an implicit equation for y of x is given by some function f of x and y equals 0. We usually have implicitly y equals y of x. How do we calculate dy by dx given this function? Let's use our rule for differentiation to calculate df by dx. So it seems a little bit strange to do this because I know that this is 0 since f is 0, but let's go ahead and use a chain rule anyway. So using the chain rule, I have that this is equal to partial derivative of f with respect to x times dx by dx, which seems a bit silly, but that's just 1, plus df dy times dy dx. And what I can do here is rearrange this now for dy by dx, and that's just equal to minus df dx over df dy. And so this gives a simpler way now to calculate the derivative of an implicitly defined function. So the way we were doing this before was to calculate the derivative with respect to x and then rearrange it, I can just now use this formula and the fact that we now know about partial derivatives to write down immediately df dy by dx is minus partial with respect to x on the numerator, which is 2x sine y, divided by the partial with respect to y on the denominator, which is x squared cos y plus 1. There are other forms of the chain rule that we often need to use. For example, say we have a function z equals f of x and y, where x and y are themselves related to two other variables, u and v, then what we have is the chain rule as follows. dz by du and dz by dv, where these partial derivatives mean they're taken with v and u held fixed, respectively. So dz du means a derivative of z with respect to u with v held constant. This is dz dx, dx du, plus dz dy, dy du. And again, the partial derivatives here mean dz by dx means a derivative with respect to x with y held constant. dx du means v is held constant. dz dy means x is held constant. And dy du means v is held constant. Okay, so note in each equation, dz du, dx du, dy du. In the second equation, dz dv, it's dx dv, dy dv. These formulas come in useful in all sorts of ways. In fact, when you do thermodynamics, you'll see these sorts of formulas come up all over the place. They're actually also useful for changing coordinates. In 2 dimensions, we're used to thinking of the point xy being described in Cartesian coordinates, but we could also use polar coordinates, where we label the point using the distance r from the origin and theta, the angle to the x-axis. And the coordinates are related. So for things with a cylindrical symmetry or circular symmetry, these are often a more appropriate coordinate system to use. We can use our chain rule to change coordinates. If we know z is a function of x and y, we can calculate its derivatives with respect to r and theta as dz by dx times dx by dr. Dx by dr is just cos theta. And dy by dr is sine theta. So dz by dr becomes dz by dx cos theta plus dz by dy sine theta. dz by d theta is dz by dx times minus r sine theta plus dz dy times r cos theta. We'll come back to these formulas when we look at integration over 2 or 3 variables.